15.4, Titration pH Curves. On the worksheet, do all the worksheet. You're going to do an entire pH curve problem. Now, you'll notice, or I probably have told you beforehand or whatever, that we skipped a lot of stuff in the notes. We skipped all of 15.3, buffer capacity, and more buffer calculations. I might talk about one or two of those, but capacity is no longer on the AP, so I'm not going to put it on there. I'm not going to do it. This is really important. Titration and pH curves. This is something that you need to know how to do. Well, I'll just tell you, what in the world do I mean by titration? Okay, there's a picture or a diagram there, and we remember from last semester we talked about these. This is called a burette. You see there's two burettes there. One of them would have acid and one would have base. This one, it says it has, here, well, it just said acid and base. It doesn't say which is which. Like you might have HCl in one and NaOH in the other. Now the thing is, you pour acid into one, and then it measures drop by drop how much acid you put in there, then drop by drop how much base you put in there until you get to equivalence point. We call it when they're supposedly going to be equal stoichiometrically in ratio, in mole ratio. Now, here's the deal. A burette can read, like a burette when it's full, it'll say like, at full it might say all the way to the top 0 at the top. And it goes down, the numbers go down different than what you see. So when you pour it out, you see how the numbers change. I think if I'm right, I don't know if do they all do that? Well, the point is, if you fill it all the way up to 0, and then you open it up and you let some pour out, and now it goes down to 5, it means you poured out 5 milliliters. Or down to 10, you poured out 10. But, you know, in case you have a burette written differently, all that really matters is, let's just say that you started at, I don't know, I'll go the other way around. Just say it was 12.5 milliliters here, and you had the chemical in there, and it had the little burette, and you poured it into this container, and you drop by drop, you send it out. So you start at 12.5, that's initial. And then it goes all the way down to, we'll just say, you stop at 6.3. Well, then how much did you pour into there? We just subtract them. Okay, so 5 minus 3, 2. 6.2 milliliters will be delivered. But I'm just telling you that I've seen most burettes, they have the numbers written the other way around, so you'll know exactly how many you added really easily because it'll be the number you see there. But always, on every lab, you always write down the initial volume reading and the final volume reading on the burette, and you subtract them. So they could do that. They could give you a question. They could show you a burette and say, you know, here was the initial number like I showed you. Here's the final, how much it was poured into there. Okay, now how will you know in an experiment if you did it right? Okay, I'll show you this. I actually have some chemical with me here, and I'm going to try this out. I've done some of these with the UCLA. This ought to work, but yeah, this ought to work. Okay, so this is a tube. It looks pretty dirty. Got chalk dust. Everything's got chalk dust in this room in here. Okay, I'm going to put some hydrochloric acid, HCl, inside here. So it says it's 0.50 molar. Not too bad, okay? So I'm going to put that in there. Now, there I'll put about that much of hydrochloric right there. Okay, now what I'm going to do, I ought to put even less, but it doesn't matter. Okay, this is an indicator chemical. You see it has no color. There's a liquid in there. Can you see that? Yeah, you can see it there. It's called phenolphthalein. Oh boy, let's find the name. There it is. Wow. Phenolphthalein. Phenolphthalein. Okay. Now, if you put a drop of phenolphthalein into water, it is this color. Colorless. If you put it into acid, it is, I'm going to put a few drops. 1, 2. Oh, actually, it should be colorless. Oh boy. Except, you know what? This must be really strong. It's kind of hard to explain. The phenolphthalein is supposed to have no color. Let me, I'm going to pour some water in here to see if that helps a little bit too. I have a cup of water. Yeah, so I poured a cup of water and it looks a little cloudy. It's not supposed to be cloudy. Phenolphthalein is supposed to be colorless when you put it in acid or when you put it in water. Now it looks better like that. Okay, but now what if, okay, so right now I've got my acid. And let's just say I had, I don't know, 12 milliliters of 0.5 molar HCl. So how many milliliters of NaOH do I need to add to this if the NaOH is also, well, just say it was 0.75 molar. Okay, well, how would you know this? Well, as you add the NaOH, what's going to happen is, can you see when I add a drop what happens? That is the color that phenolphthalein has in NaOH. If I add it to a base, it gives you a magenta, a purplish color. Now, I'm going to keep on adding it. And what you do is you add it. The top part is basic, but then the acid eats it up. Okay, I'm going to put a bit more. But you want to do it just until it changes color, until it stays magenta is the name for that, or faint pink. You don't want to make it dark. If you make it dark, then you've done it. Oh boy, I'm getting close. You can see one drop is starting to do it now. One drop more, one drop more, one drop more, one drop more. I'll put 2 drops. Uh-oh, that might do it. Let's see. Nope, it's still going to eat it up. Oh, I overdid it. Ah, too bad. I know it looks really cool, that color, but it's not supposed to look like that. So what should happen in a good lab technique, if you're having good lab technique, then what's going to happen is it's going to be a very faint color. I'll create it here if I can. Oh, you know what I could do? I could just add some acid to it and go back the other way. Yeah, I could do that. Let me find the acid. Yeah, let's just do that. Okay, I put a little bit of water in there to help it a little bit. But if I add some acid now, let's see the color. Oh, it's gone. It's gone now. Oh my goodness. I could do this all day, couldn't I? I don't know. I didn't know I was going to do this in the video, but we don't get to have any labs, so let's try it again. I'm going to try 1 drop of NaOH. 1 drop. 1 more drop. I think it was really 2 drops. 1 more drop. 1 more drop. 1 more. 1. Can I even make it happen here? Oh boy. Well, yeah, kind of. Oh well. Well, you want it to be the faintest pink, that when you hold it against a white piece of paper, you can see just a little bit of pink color. That means you did the best lab technique. Okay, here we go. So, the titration is the process of adding one solution, like it could be HCl to NaOH or NaOH to HCl. One solution to another by a burette. Really, you could call it titration if you mix. It doesn't have to be acid and base, but it also could be anything, any 2 chemicals. It could also be adding to a solid. I guess you could call that titration as well. The titrant is the chemical that's in the burette going down, and the analyte is the chemical you're analyzing. They don't really use those words too much. Okay, so I have already done, in the last video when I went over different types of reactions, when you mix 2 chemicals together, what's going to happen? Are you going to have an acid system? Does the acid overtake the base? Or does the base, when you mix them together, does the base overtake the acid? Or are they neutral? Are they both equal? And, or is it a weak acid, buffer, all that kind of stuff? So you're going to see all that happen in titration. Well, I'm going to jump over to, first I'll do this one, which is a strong acid and a strong base. Now, I'm probably going to have to make more than one video of this, I know too, as I'm doing this in parts. But this is one of the easiest ones. Now, for some years, I always thought one day they're going to have you do a lab, or do a question on the AP and make a graph of a titration curve. And they did do it a few years ago, finally. But they give you, on multiple choice, they always give you questions like this and ask you what things are. But if you look there, this would be, what you do here is, on one side, this is the pH, 0 to 14. Down here, it's going to be the volume of NaOH that you add. You add 0 volume, what's the pH, okay? Then when you add whatever it says there, 25, 50, 100, 150. I might have to change those numbers. I can remember, I don't have my notes because they're still locked up at school, but oh well. But anyway, and then that's all. How much did you add to the acid, and what does the curve look like? Okay, so I'm going to show you. This first one is a strong acid being added, no, a strong base being added to a strong acid. You can look at the graph and know which one was added because it's on the bottom, NaOH, how much was added. And letter A says this. So I'm going to try and draw, we're going to try and draw the graph. You know what, I'll probably draw it on this graph paper. I mean on my lab paper. That'll actually be a good thing. Okay, question, it says you have 50 milliliters of 0.200 molar HNO3. Is titrated with 200 milliliters of 0.100 molar NaOH. Okay, the titration was carried out drop-wise. And what that would mean is you can set the dial or the little valve on the burette tube so it just drops 1 drop, 2 drop, 3, 4 at a time. You know, gravity's pulling it down. And then you can watch what happens. Now that we have computer, we can do a whole lot of cool things with that and like watch the computer graph it for us. But anyway, we don't have that all set up now. So anyway, calculate the pH for the following points in the titration. Now, you don't have to get every single point, but you need some important points. Well, first of all, I'm going to show you something. What's going on is we're adding NaOH to HNO3. NaOH plus HNO3. What is that going to give us? It's going to give us NaNO3 and water, HOH. Now, the other thing is, imagine this. So, if I have my little curve, well, I could draw it there. Well, I don't know. Maybe I'll just draw a little container. Here's a flask. This has in it HNO3, and it's 0.200 molar. We know that. All right? And it's 50 milliliters of it. And we're adding the NaOH into that. Oh, that's a sad-looking burette, but oh well. NaOH, that is 200. Well, we don't know. We have up to 200. That would be a really big tube. But it's going to go drop by drop. You're adding 0.100 milliliters to that. Okay. So let me tell you a little something about this. When you probably are not going to see on the AP a strong acid and a strong base mixed together in a titration curve. You might. You could. And now that I say it, yeah, you probably will. I mean, now that I'm saying it, you're not. Maybe you will. But strong acid to a strong base or strong base to a strong acid. Let me show you what's going to happen. Okay, if you have the pH curve, I'm going to give you a general answer before we do anything. Here's the pH and the volume of NaOH added. Now, in the very beginning, before you put any NaOH, all you have in here is acid. Here's the NaOH. So how would you find the pH of an acid, of a strong acid? You just take the negative log of 0.200, remember? And in fact, we can even do that. But I was going to tell you, even without doing it, it's going to be a really low number. Like if this is 7, and that's 14, that's 0, your pH is going to be like down here, like 1 or 2 or something. So 0.200 log negative, it's actually 0.70. The pH is 0.70 of that. The negative log of 0.200 is 0.70. Okay? So you'd start down here. Well, anyway, here's what's going to happen in the pH curve. You're going to add, well, it will be going up a little bit. As you add the NaOH, it'll be getting a little bit more basic, but not very much at all, because all the acid is going to be eating away at every drop that comes down in NaOH. So it's almost like it just gets canceled out. But suddenly, you're going to get to a point to where the acid and the base are equal. And when you do, it's going to jump all the way up. It'll jump all the way up. Well, we'll stop it here for a minute. If they're exactly equal, this line is almost a straight line, but not quite. But it's just nearly a straight line. When they're equal, a strong acid and a strong base, the pH will equal 7. Okay? I'll show you why in a minute. Because it is pure water. And in water, the OH negative equals H plus. And so if they're equal, then it has to be 7. So that's going to be pH of 7. But now, so you're going to add 1 drop, 2 drop, 2 drop, whatever, 20, 30, 40, 50, 60, 80, 100, 1,000, 2,000, whatever. All these drops you're adding, and it's barely changing. But then suddenly you're going to hit a drop, and it's going to shoot way up. And then if you continue to add more NaOH, it will go all the way up, and it will be almost like as basic as that can be, 0.100 NaOH. if I take 0.100 and take the negative log of that, that's a 1 POH, which is a 13 for the pH, which means right under there. And it'll be about like that. So here's what I want you to see. If you see a curve that looks kind of like this, acid, pH is really low, base, and neutral is in the middle of that line. Acid, base, neutral. Okay, what would happen if they said the other way around? We're going to add HNO3 to NaOH. Well, in that case, what would happen? It will be the volume of HNO3 added. I'm writing it so messy. And in that case, you'll start off your pOH, you'll be very basic in the beginning, then it'll go down, and then it'll come across and become very acidic. So actually, I could have made it almost equal to that. Let's just say it's the mirror image of that. So look at that. That would be acid, and it becomes basic. So a base was added to a strong base was added to a strong acid. That's what it's going to look basically like that. Okay, it'll be a bit more curved than I'm showing you, not so zigzag, not so like square looking, but it'll be it will come up probably more than that, and it'll be a little bit more diagonal than I'm showing you. And then this one will be the opposite. So just by looking at the shape, you could know that. There's two ways you can tell it's a strong acid, strong base, or strong acid. It's because it's very, very low pH, like really strong pH acid, and a really high pH for the base, okay? If it were a weak acid, it probably wouldn't be this low. It would probably be a little bit higher, like 3 or 4, maybe near the middle there, okay? It would start off there if it were a weak acid. Or if it were a weak base, it might end like, wouldn't end so high up. It would end a little bit like over here, okay? So that's a couple things to know. All right, so let me go on and find the points, and we'll make this one sketch on the paper. But this method will show you how we're going to do the other ones after it. Now, these are easy titration curves to make for this one. So what I'm going to do, the first point, it says, what's the pH before anything's been added? And I already showed you that. All right, so letter A, before the system is strong acid, 200 molar HNO3. Before adding anything, it's only an acid. So the pH will be negative log of H3O plus, and you can say, or H plus, you want to put H plus, feel better with that, which is going to be 0.200. And we know that H plus equals HNO3 because it's a strong acid. So negative log of, I did it on the paper a moment ago, I'm on my calculator, 0.200, and I told you it was 0.70. Okay? 0.200 log negative 0.70. Actually, I can have one more sig fig, 3 sig figs, so 0.699 is the pH. Okay, that's the pH before you add anything. So what you could do, I don't know if, we'll see if this graph works out. So it's less than 1. Uh-oh, does this pen work? It does. Well, I just made a little red mark underneath 1, like 70%, whatever, 0.70. So before you add anything, that's your first pH right there, okay? Then it says, what is the pH after 10 milliliters have been added of the 50? I might not even do that. Well, I'll do that. Why not? What is the pH after 10 milliliters have been added? Okay, you could do this as many as you wanted to for as many points, but you don't really have to do that. So B, let's just do this one at least. Okay, 10 milliliters of 0.100 have been added. Remember, I'm going to make a stoich box, and I want to find out what are the moles. So if I have 10 milliliters of NaOH, then I'm going to say, okay, 1,000 milliliters for 1 liter of NaOH. And 1 liter of NaOH has in it 0.100 moles of NaOH. And so what is that going to give me? 10 times 0.10 divided by 1,000. I don't want to try to do all that in my head that quick, but 1 times 10 to the negative, or 10 to the negative 3 moles. Or maybe I'm going to make it 0.001 moles of NaOH. Just to play around with the math a little bit better. I don't know. 0.00100 moles. 10 times 0.100 divided by 1,000. Yeah. Either one's okay. It might be a little better that way. Okay. So I'm going to add 0.00100 moles of NaOH. Now, how much HNO3 do I have to start off before? Okay, so we're adding that, and we have 200. Well, oh, not 200. 200 went with the NaOH. We don't have 200 yet. We're only using 10 of them. So this number doesn't really mean much unless you want to do the very last point. But it means you have up to 200. 50 milliliters. So 50 milliliters of HNO3 do the same thing. Okay, 1,000 to 1. Then, but you use 0.200 for its moles. And so it's going to be 50. That 5 looks really weird looking, doesn't it? Almost like a 6. And I don't know if that's better. 50 times 0.200 divided by 1,000. It's 0.01. 0.0100 moles of HNO3. Okay, so let me erase that to not get mixed up. Okay, NaOH. And then here's your HNO3. 50 milliliters are in this container. They're 0.200 molar, so 50 over 1,000 times 0.200. 0.0100. All right, 0.0100. All right, so here's what's going on. You start off, you're putting this many moles with that many moles. You have none of that, none of that. What's the change? Well, again, the limiting reagent will be the smaller one. So obviously, all the NaOH, just like you saw me put the drop in there, and when I first put the first drop, it was real pink, but then it just disappeared immediately because it got eaten up by this. That's O100 and OO100. So that's a very small amount. Okay, so minus this, that's your limiting reagent, and this will be the same thing, minus 0.00100. All right? I guess I could line it left, not too bad. That'll be plus 0.00100, and that'll be plus 0.00100. Now, after, I'm going to have, well, it looks like that's 0, and that's going to be 0.0090. So 9 times 10 to the negative 3 is 0.0090. Yeah. Now, if you want to write down 1 times 10 to the negative 3, and I might do that next time, 1 times 10 to the negative 3, and then 1 times 10 to the negative 2, you can do it that way as well. You don't have to do it this way. And then it'll be 0.00100. Okay, so the main thing is now, when you're finished, we want to find what is the pH after you add it at that very moment. At 10 milliliters added, 10 ml added, pH will equal, okay, it's the negative log of the HNO3, which is H+. But now you got to remember this. It's going to be the molarity now. It's going to be 0.0090 moles. But then what's your volume now? Your volume, you started with 50 milliliters of HNO3, right? How much did you add, though? You added 10 milliliters. So 50 plus 10 is 60. So you have 60 milliliters. But then you got to have it in liters, so divide by 1,000. So look at that craziness. So after 10 milliliters are added, you got to take moles. This is how many moles of HNO3. Only this will affect your pH. That will not affect your pH. Remember, the NO3 is not the anion of a weak acid. Only the weak acid conjugates. NO3 is a conjugate this from a strong acid. It will not affect pH, and water won't affect it either. Okay, so what I'll do is, I think I don't know. I might keep those numbers down here for a minute just to save me some time. But I'll have to do something here. What is that going to be? 60 divided by 1,000 is 0.06. All right, so you on your paper, if you have room, try to go below it. I hope you didn't do what I did, but it's 0.060. 0.0600 liters. Okay, so now mole divided by liter. is 0.15. All this is 0.15. So the negative log of 0.15 is 0.82. So the answer is 0.82 for your pH. I guess that's 2 sig figs on that part. So 0.82 pH. All right, so we did all this work just to find out that at 10 milliliters is 0.82. So what does that mean? It means that on my little graph, we started with 0.70, right? 0.699 or whatever. Now, after 10 milliliters are added, so you can go all the way up to, where would 10 be? And I didn't do a very good job. I got 25, so half of 25 would be, what, 12? So a little bit before that, I'll go up, and it's going to go up to 0.80. So, kind of goofy, 0.80. So I went, again, I try to go 10 milliliters. Where would that be? It'll be numbered better if it's doing AP, and on your worksheet, it'll be labeled better. This is 25 milliliters, so half of that is 12.5. So I went a little bit before that, and I went just a little bit above that, but I still want to be underneath the 1 line. So there it is. This line is going to be pretty much straight, as I told you at the beginning, okay? But that just shows you how you get a point on the graph. Now, the next one says, what will be the pH? C, this is an important one, at equivalence point. You don't have to do the 10 milliliter one probably, even on an AP you wouldn't, but I just wanted to show you to get you used to how you do this. But how would you do it at equivalence? Well, here's a fun one to do. At equivalence point, that means that the moles of NaOH that you added equal the moles of HNO3, okay? Equivalence point. So here's the way you can actually do equivalence point. I'm going to erase this. Now, you might want to make a new box, and this is letter C. This is where a chalkboard will come in handy for me now. Okay, at equivalence point, we started with only HNO3, remember? Forget the other added yet. We only had HNO3 0.200, and in there we had 50 milliliters of at 0.01 moles. Okay, at equivalence point, that means that I'm going to be perfectly matched NaOH, 0.0100 moles. Equivalence point, it has to just equal that, because that's by definition. Now, okay, let me take that, let me add a little thing. Because it's a 1-to-1 ratio, it has to be equal, all right? If this had been, for some reason, a 2 NaOH added to that, well then, at equivalence point, you'd have to have 0.0200 of that. You'd have to double it. So it's kind of like the mole ratio. You know, if I change this, moles of HNO2, go to HNO3, sorry. It looks like a 2 now. Moles of HNO3 to moles of NaOH, you'd say, well, 1 mole of HNO3 gives requires 2 moles of NaOH. So I would say I need 0.0200. So if there's a 2 there, it would be a 0.0200, okay? But it's a 1. And then one more thing to tell you. It's going to always be 1. It's supposed to be for AP. They're only going to give you 1-to-1 ratios. So, but I wanted to tell you that in case you decide to ever use this method for another like a stoichiometry limiting reagent. You can do that, and you just got to watch out for the coefficients if there are any. Okay, here we go. So at equivalence point, one thing we know is the moles are equal. And so I'm just going to go down, and then the limiting reagent is the same number, 0.0100, 0.0100, 0, 0, plus 0.0100. And since this does not affect the pH of water, then the pH will be 7. It's just going to be 7. Because NaOH and HNO3 are both equal. They're equaled out. But what is the volume at equivalence point? Now that's an interesting thing to see. What will be the volume at equivalence point? And you're going to remember this from last semester. What volume of NaOH would be needed to neutralize or to neutralize or reach endpoint, reach equivalence point? Well, what volume of NaOH will be needed? Okay, so in other words, I want to get milliliters of NaOH right here. And I'm going to start with, on this side, I'm going to start with what I had of HNO3. 50 milliliters of HNO3. Can you remember this from last semester? From milliliter, we go to liter. 1 is 1,000. Then from liters, we go to mole. And it's HNO3 to start off with, okay? So, 0.200 moles of HNO3. Can you read that real small? 0.200 moles of HNO3. I'm trying to fit this in here. For 1 liter of HNO3. And then, you need 1 mole of mole to mole. Moles of HNO3 go to moles of NaOH. I'm going to show you a little shortcut thing later. 1 to 1. And then, moles of NaOH go to liters of NaOH. Oh no. And then liter to milliliter. Wow. There is a shortcut. And I'm going to show it to you, but okay. 1,001. And the NaOH is 0.100 for 1 liter. All of that work just to get a number of milliliters. And let's see what it is. So 50 times 0.200. The thousands are going to cancel. And the ones are going to cancel. And then divided by 0.100. So it's, wait a minute, 50 times 0.200 divided by 0.100 is 100. Yeah, I multiplied it wrong. 50 times 0.200 divided by 0.100, it's 100 milliliter is the answer. So what volume is needed to get to equivalence point of NaOH? What volume? Now again, don't worry about the fact they said you have 200. No, you don't. You have it available. But we're gonna. How much of that do I need to add? And it ends up being half of that. Okay. So or double that one. So 50 milliliters of 0.200 molar. You got to go. Milliliter, liter, liter to mole, mole to mole, mole to liter, liter to milliliter. It's 100 milliliters. Now, so my graph is not going to be perfect, but here's what oh, I didn't show you. That's the first part. I'm going to have to just erase this. I didn't want to, but I guess I have to. Okay, I have to come back to it in a minute if I've got to rewrite it. So the pH, the system is neutral. Strong acid, strong base. So pH equals 7. You could just say that, 7.00. Now, if you wanted to, you could say pH will equal the negative log of H plus, and it will be negative log of 1 times 10 to the negative 7. Remember, at 25 Celsius, H plus will be 1 times 10 to the negative 7, OH negative 1 times 10 to the negative 7, and together they'll give you 1 times 10 to the negative 14. So that has to be the pH. Well, you can know. You can remember OH negative times H3O plus equals 1 times 10 to the negative 14. If they're both equal to each other, at 25 Celsius, that's always true. So if they're both equal, then you could say X times X equals that, so X will be 1 times 10 to the negative 7. So that has to, you don't have to actually write that down. But that's why it works out, okay? I mean, if I want to do X times X, so X is X squared, X equals 1 times 10 to the negative 7. At 25 Celsius, that will be true. Because if there's no OH and no H plus, then that means that they have to, that there's no excess OH and no excess H plus. In water, that will be true. Okay. All right, so here's the deal. 100 milliliters, at 100 milliliters added, the pH becomes 7. So now we get another point on the graph. And again, it's not a perfect, the way I made this, but it'll work out. So at 100, I can go all the way up to 7. Isn't that fun? I can just jump up here. All right. So I can pretty much trust that it's going to be pretty much a straight line going this way. And then around here, it's going to start shooting up like that. And they'll probably go up, and then they'll move over, okay? So that's how your curves are going to look so far, all right? Now, let me see. I'm going to have to continue on with the next part. Well, the last one says, what's the pH after all of that has been added? And I really don't even much want to do that, go through the whole thing, the math of that again. But after all this been added, I think you kind of get the idea of what's going to happen. I guess I'm going to have to continue it on the next section part. I'll do it. I'll get through it because you need to see these. All right, I'll do a part 2.